So let's do analysis for one of those systems, combined heat and power generation. Okay, let's do this example in the book. Okay, so I made a sketch so that we can understand what's going on. So he require for the turbine, he want to produce this much BTU. He can say kilowatt hour, he can say joule. Anyway, so he used BTU. He said in order to generate this much BTU, how much CCF of natural gas we need. Alright, so he's asking about Q added. He's giving us work net and he's asking for Q added. And he will use those numbers in this example. So one of those numbers is ETA electric, 30%. So he assumed this power plant, this gas turbine cycle, compressor, combustion chamber and turbine have an electric efficiency of 30%. Okay, so that include the thermal efficiency and like mechanical losses in the bearing and generator efficiency. So it's the plant efficiency, ETA electric. So that's easy. We all remember that. What is the definition? What is the definition of this ETA electric? So this ETA electric is simply work net over Q added. So since I have this and I have this, it's very easy to calculate the Q added. Okay, and so that's what you see over here. So the natural gas required will be electric energy required divided by ETA electric. Here is the BTU, here is 0.3, and you get the natural gas required in BTU. So now for the CCF, that is 100 cubic feet. Okay, and our book used this conversion. He say 100 cubic feet is 10 to power 5 BTU, is 103. But 100,000 is okay. So let's remember 100,000. Okay, because also in the final you will gonna use your textbook. So it's gonna be 100,000. So if you do that conversion, you will find out that the natural gas required is 1.9 million CCF. Okay, very good. The second part, in his calculation he said, so because my efficiency is 30%, all that natural gas that I'm burning, I get only this much BTU, and there's tons of energy that will be released in this host. How much? The remaining of the 30%, right? So 70% is basically going out here. So he is saying, well, if I use a heat recovery boiler or a heat recovery basically unit, a heat exchanger kind of, can I just send this exhaust and try to use this for heating? So I send water in, the water will get hot and come back to me hot, and can I use it for heating, for example? Or I can use air heat exchanger. The point is he's asking for how much we can recover. Recovered energy, recovered thermal energy. So we need an efficiency for that ETA recovered, and that efficiency is actually not of it's not a factor of this, it's factor of Q added too. Just like ETA electric tell you how much is coming this way, the ETA recovered by definition is how much of the natural gas that we burn will be recovered. And so he will use see, this is ETA recovered over here. So in the textbook he used the number a little bit wrong, so be careful of this. So ETA recovered, I mean he said ETA recovered, but then he ended up writing ETA electric. It should be ETA recovered. And so in that range, 0.35 to 0.5, he used 0.34 ETA recovered. So out of the 1.9 million CCF, if you multiply by ETA recovered, you get how much thermal energy is recovered. Okay, make sense? So why not all of it? Why I just said that 30% is going this way and 70% is going that way? You will not be able to recover everything. If you recover everything over here, then the air is leaving at room temperature to start with, and don't forget there is 10% that doesn't burn to start with and is moving as unburned hydrocarbon. So there is no way you can recover everything. So you see the typical number is 0.35 to 0.5. So using 0.34 you get this much. Okay, And again, you can either use it in CCF or use it in BTU, but he asked for, or he's trying to do analysis in CCF, which is how much? 10 to power 5 BTU in our book. Very good. The next part, so this is what we figured out. With if you use 0.34 of this number, you get this recovered as thermal energy recovered, right? And this much as electric power. Very good. So now he's saying that energy that I just recovered, if I was gonna, rather than using, what is that called? This is a combined heat and power system. That energy, if I have just got it from burning natural gas, without any power generation, just burning natural gas in a boiler, getting my 660,000 CCF, how much natural gas needed? So that would be the equivalent natural gas recovered. When you put that system and you recover this much thermal energy, so he's saying, well, how much then natural gas did I save? Is it exactly this much? No, it's a little bit bigger. By how much? By the boiler efficiency. Any boiler has an efficiency. Unburned hydrocarbon, heat losses from the wall, all those things that basically doesn't make you burn at 100%. So that is easy. That efficiency by definition is the output divided by the input. So if I want to this, then I will divide the output over eta boiler. Okay, just one more thing to remember. This, what is that? That's what we recovered by using a combined heat and power system. So he's using a boiler efficiency of 85%. So the 660 divided by 0.85, then you just, this is the equivalent natural gas recovered. Okay, 776,000 CCF you just recovered by doing this. So now, if your application, if that hotel or that hospital is already burning this amount of natural gas for heating, by doing this, you got it. Okay, you don't need an external boiler anymore. You can shut it down. And if they have used, if they are using more than this, then at least you, by doing that and recovering some thermal energy out, so you will release a little bit their load. So natural gas bill will not be as much as it used to be, right? By how much? This is the saving. So in the book, then he will in the book you will see at the end of the example, he's saying now, so now the natural gas that I need to buy is what I'm buying originally, right, for my heating, plus the amount that the new CHP, the combined heat and power cycle require, minus the amount that I'm saving. That amount that is recovered, thermal energy recovered, natural gas, this one will be subtracted from this. Okay, so I added a little bit because I'm making power, but I saved of the heating part. Okay, of course, by doing this, then I have to pay for this, for the turbine cycle, right? But the saving that we are doing will end up paying for it over the year. Alright, so you can see over here he's now calculating the natural gas cost. All this natural gas he's buying, here is the cost. So he's using 26 cent for CCF by CCF, adding 1.5 tax, okay, sale tax. And so here is the natural gas cost, and he's trying to calculate the operating and maintenance cost, and he's saying it's reasonable to assume that a gas turbine will have 1 cent per kilowatt hour. So here is how much kilowatt hour it's producing, multiplied by 1 cent. This is how much maintenance. So the total cost would be the gas that you are paying and the maintenance cost. This is the operating cost. Alright?